everyone, thank you so much for joining this video. Today we're going to be looking at substitution reactions. So we're going to be learning about how water, ammonia and chloride ions are monodentate ligands, and then we're going to look at how ammonia and water are similar in size, and when we exchange these ligands there's no change in coordination number, and how substitution may be incomplete. We're also going to look at how the Cl- ligand is larger than the uncharged ligands, and how the exchange of water by Cl- can involve a change of coordination number. We're then going to look at bidentate ligands and multidentate ligands, and also look at the example of heme. And then we're going to look at how oxygen forms coordinate bond to Fe2+ in hemoglobin, enabling oxygen to be transported in the blood, and how carbon monoxide is toxic. We're then going to look at the chelate effect, and by the end we should be able to explain the chelate effect in terms of the balance between the entropy and enthalpy change in these reactions. Now we're going to talk about the different types of ligands that we have. So the first type is monodentate ligands, and examples of this are water, ammonia and the chloride ion, and these can only form one coordinate bond per ligand. So for example, if we had chloride, it only has these 2 electrons which it can donate to something else, and so that's why it's a monodentate ligand, because it can only form one coordinate bond because it only has one lone pair of electrons. The second type is a bidentate ligand. An example of this would be the ethane dioate ion or the 1,2-diaminoethane. And these both have 2 atoms with lone pairs and can form 2 coordinate bonds per ligand. So if we see here the 1,2-diaminoethane example, we've got a pair here and a pair here. So that means that we can form 2 coordinate bonds with a ligand, and the same with the ethane dioate ion. And then the third type of ligand is a multidentate ligand. An example of this is EDTA, and this is the only one that you really need to know. And it can form 6 coordinate bonds per ligand. So the ones which bond are the ones on these oxygens with the negative charges, and also the nitrogens. And so on the right we've got a diagram of how it forms coordinate bonds to the ligand, because it's 3D, so it can be quite hard to imagine how it kind of loops round. Now we're going to talk about substitution reactions. So water, ammonia and the chloride ion can all act as monodentate ligands. However, we're going to just look at ammonia and water for now. So these 2 ligands are very similar in size and they're both uncharged. And so what that means is that when we exchange them, it occurs without change of coordination number. And the definition of the coordination number is how many coordinate bonds are attached to the central metal atom or ion. So for example, we have this cobalt ion with 6 waters attached, and then we react it with 6 ammonias, and we see that the waters have all been substituted by the ammonias and nothing's changed. So the coordination is the same, coordination number. So the coordination number in the first ion is 6, and the coordination number in this one is also 6, because they're monodentate ligands, so they form one coordinate, and there are also 6 waters, so that's 6 coordinate bonds, and there are 6 ammonias, so that's also 6 coordinate bonds, and so 6 waters are taken out. So the definition of substitution is a chemical reaction where one functional group in a chemical compound is replaced by another functional group. So in the example that we saw before, all the waters are being replaced by ammonia. So ammonia is substituting water. However, the substitution may be incomplete. So if we look at copper instead of cobalt, so we start off with a copper and 6 waters complex, and we add 4 ammonias, but this time only 4 of the waters get substituted by ammonias, and so we're left with this other complex of Cu H2O NH3 4 2+, and then the 4 waters which have been substituted out are left as a product. And we'll learn later that this first complex is actually a pale blue solution, and this new complex that just formed is a dark blue solution. So we'll be looking at that a little bit later. So now we're going to look at chloride ion reactions. Now the chloride ion is another monodentate ligand, but it reacts slightly differently to ammonia and water, and now we'll see why. So when we add a high concentration of chloride ions, either from concentrated hydrochloric acid or saturated sodium chloride, to an aqueous ion, a ligand substitution reaction occurs. And this is again where a ligand replaces another ligand which is already bonded to a transition metal ion. And the Cl- ligand is larger than the uncharged water and ammonia ligands. And so therefore, ligand exchange can involve a change of coordination number. So what actually happens is that the coordination number goes from 6 to 4 when we're substituting waters and ammonias for the chloride ion, because the chloride ions are much bigger, so you can't fit as many around the transition metal ion. And so here we have 3 examples. The first one is copper with 6 waters and a 2+ charge. So this is the first complex that we have. And then we add 4 chloride ligands to it, and CuCl4 2- forms. And the difference we'll see is that the first complex will be a pale blue colour, whilst the CuCl4 2- will be a green yellow. And we'll be seeing all these results a bit later on, but this is just to get the hang of writing out the equations. So we know it's a 2- charge because, so we know the charge of the copper is 2+ and the waters are 0. That's why we have this charge here of 2+. So we have a copper which is 2+, and we have 4 Cl-. So one Cl- is -1, so 1-, and then we have 4 of them, so that must be 4-. So the overall charge will be 2-. And then this 6 waters will be taken out of the complex. So the chloride ions have substituted the waters. And we can see that the coordination number of this complex is 6 because each water can coordinate bond once, and we've got 6 of them. So the coordination number is 6, and the coordination number of this CuCl4 2-, which has been formed, is just 4 because each Cl- can form one coordinate bond, but we've only got 4 of them. So we've got an overall total of 4 coordinate bonds around the central metal ion. And it's the same thing for the cobalt and the iron as well. So now we're going to talk about the second type of ligands, which are bidentate ligands. So examples of bidentate ligands are ethane 1,2-diamine and ethane dioate ion. And they both have 2 atoms of lone pairs, which can form 2 coordinate bonds per ligand to the central metal ion. And so, as you can see, with the ethane 1,2-diamine, there are 3 bidentate ligands in this complex, and they bond twice to the metal ion. And so the metal ion still has, well, the complex still has a coordination number of 6. And then for ethane dioate, it's the same thing. And also the metal ion, the complex, still has a coordination number of 6. And so we see that bidentate ligands can substitute water ligands. So we start off with copper, coordinate bonded to 6 waters. And then if we add 3 of these ethane 1,2-diamines, then we form a copper with the ethane 1,2-diamines attached. And so we only need 3 of them because one of them attaches twice. So 2 times 3 is 6. So the coordination number hasn't changed because the coordination numbers of both complexes are 6. And so the 6 waters have been substituted, and so they come out. And it's the same for ethane dioate as well. And again, to get the charges, we just look at the molecules. So for this one, the copper 2+ is 2+. And then this is neutral, so it's 0. So that's why the overall charge is 2+. Here we have 2+ for the copper, and ethane dioate is a 2-. You have to remember the charge of all these different ligands, because when you form equations, you need to know the charges of the complexes that you form. And so because we have 3 of them, that's 2 times 3 is minus 6. So we have 2 minus 6, and that's how we get the overall charge of 4 minus. And then again, the waters come out. Partial substitution of ethane diode ions can also occur with copper 2 plus ions. So we have the original complex with copper 2 plus and 6 waters attached. And then we react this with 2 of these ethane diode ions, and we form this new complex with 2 of the ethane diodes and 2 waters, because these 2 ethane diodes can coordinate bond 4 times, and then the waters can form 1 coordinate bond each. So that's another 2, and so that's how the coordination number still remains as 6. And so again, the 2 minus comes from the copper 2 plus being plus 2, and the C2O4 minuses being 2 minus each, and so that's 4 minus, and so that's how we get the 2 minus. And then 4 waters come out because we originally had 6 attached to, well, coordinate bonded to the copper 2 plus ion. And now we're going to look at the last type of ligand, which is a multidentate ligand. Now, a multidentate ligand, for example, we have EDTA, can form 6 coordinate bonds to the transition metal ion per ligand. And a real-life example of a complex with a multidentate ligand is heme, which is found in hemoglobin, and it's an iron 2 complex with a multidentate ligand. In the blood, oxygen forms a coordinate bond to Fe2 plus ions in hemoglobin, and it enables oxygen to be transported in the blood. However, carbon monoxide, which is really toxic to humans, forms a strong coordinate bond with the hemoglobin, and this bond is actually stronger than that made with the oxygen, and so it replaces the oxygen attaching to the hemoglobin, and this means that there will be less oxygen transported into the blood and like to all your organs, so it makes it harder to breathe. So we can form multidentate complexes like this. So we start off with this complex with copper and 6 waters with a 2 plus charge, and then we have an EDTA 4 minus, which you must know about. And then how it bonds is that one EDTA ligand can bond 6 times with a metal ion, and so that's how we just have one ligand here bonding to the copper, and so 6 waters are removed, so they've been substituted. And again, how we get the charge of the complex is that copper 2 plus is 2 plus and EDTA is 4 minus, and so the overall charge is 2 minus. And you can also see that the coordination number hasn't changed, because the coordination number here is 6, because there's 6 coordinate bonds attached to the copper, and for this complex it's also 6 because the EDTA forms 6 coordinate bonds with the copper 2 plus ion. Now we're going to talk about something called the chelate effect. So when ligands are being replaced by ligands that form more coordinate bonds, the reaction is feasible. And this is because of 2 reasons. The first is that the enthalpy change is negligible during ligand substitutions because we have the same number of bonds being broken and formed. And then the second reason is that the entropy change is very positive as more species are formed. So for example, if we looked at copper, a copper 2 plus complex with 6 waters, and we added an EDTA to form a complex with Cu EDTA, and then this would be 2 minus, and then 6 waters would be substituted out. So the enthalpy change is negligible because we are breaking 6 bonds because there are 6 waters originally attached to this copper 2 plus ion, and so we need to break those 6 bonds. But then when the EDTA forms around the copper, the 6 bonds are formed again, and so this is why the enthalpy change is negligible. But the entropy change is very, very positive, and that's because on the left-hand side, the reactants, we only have 2 reactants, but on the other side, on the product side, we form 7 products. And so there's a much larger entropy because there's way more disorder because there's 7 products formed from 2 reactants. And so when we look at this Gibbs free energy change, with this equation delta H minus T delta S. Because this delta S is so positive, that means that this delta G will be very, very negative. And so the substitution of monodentate ligands with bidentate or multidentate ligands lead to a more stable complex. And so this is called the chelate effect. So now we're going to have a look at a question, and it's to write an equation for the reaction of the ions from Ca2 Na2 EDTA with PbH2O6 2+ ions. So what we have is that we have these lead 2+ ions, and we add some EDTA to it. So I'm just going to write the EDTA ion, and so this will form Pb EDTA because a ligand substitution is happening. So all the waters have been substituted for one EDTA. And so this now has a 2- charge, and then we have the 6 waters taken out. So this is the simplest equation that we can write. And then for B, explain why this reaction is feasible in terms of Gibbs free energy. So we have delta G is equal to delta H minus T delta S. And so first looking at delta H, we know that this is negligible during these ligand substitutions, and this is because we're breaking 6 bonds to get rid of the waters, but we're also forming 6 bonds with the EDTA, and so there's the same number of bonds broken and formed. And then for delta S, if we count all the products and the reactants, so products we have 7, and the reactants we have 2, and so that means that this is very positive because we form 7 products from 2 reactants. And so this means that when we look at Gibbs free energy change, so delta G, so if delta H is negligible, we can kind of count it as 0. And then so we get delta G is equal to minus T delta S. And if delta S is very positive, so it's very big, then what that means is that delta G is very, very small, and it's a lot smaller than 0. And because delta G is negative, this means that the reaction is feasible. This delta G is very negative, so it's less than 0. Before I move on to the second question, feel free to click off the video and try it for yourself first. So we're told to use the following equations to answer the questions after them. So we've got these 4 equations. And so for A, identify which, if any, of the reactions involve ligand substitution. So ligand substitution is where we replace one ligand with another ligand. So we could replace water ligands with ammonia ligands, or with chloride ligands, or some bidentate ligands, or even multidentate ligands. So for A, which ones involve ligand substitution? So if we look at the first one, that is ligand substitution because we're replacing the waters with ammonia ligands instead. So the first one is. For the second one, that is as well because the F minuses are replacing the waters, and so 2 is also a ligand substitution. For 3, we can see that it isn't a ligand substitution because we're not replacing the waters with another ligand, and so 3 is not a ligand substitution. And then looking at 4, 4 is also a ligand substitution because we're substituting the bidentate ligand, we're substituting the water ligand with the bidentate ligand ethane dioate. And so 4 is also a ligand substitution. And now for B, identify which, if any, of the reactions involve a change in coordination number. So the definition of coordination number is how many coordinate bonds are attached to the central metal ion. And so we can see that all of these complexes start with 6 because we've got 6 waters attached to each cobalt, and they're all monodentate ligands, and so they form 1 coordinate bond each, and we've got 6 of them, so that's 6 coordinate bonds. So they all start off with 6. So first we look at the first equation, and we see that CO NH3 6, because NH3 is another monodentate ligand, that means they bond once. So we've got 6 of them, so that's another 6 bonds, and so the coordination number does not change in the first equation. Then looking at the second equation, again, the coordination number does not change because each F minus bonds once to the cobalt, and we've got 6 of them. So for the third equation, we see that the coordination does not change again because actually we haven't altered all the waters which are attached to the cobalt. We have just changed the oxidation number of the cobalt ion, and so the coordination number is still 6. And then for the fourth equation, we have a bidentate ligand which has substituted the monodentate ligands, which are the waters. And what we need to remember about bidentate ligands is that they bond twice, and they form 2 coordinate bonds, to the cobalt metal ion. And because we have 3 of them, that means that they form 6 bonds altogether with the cobalt. And so again, the coordination doesn't change. So we have none as the answer for B. And then for C, in any reactions where the coordination number changes, explain why this change occurs. So we actually don't have any reactions where the coordination number changes, but we can explain why a coordination number can change. So for example, if we started off with this cobalt metal aqua ion, and say we added 4 Cl minuses to it, then what would form would be COCl4 2 minus, and also the 6 waters. So this is another ligand substitution, and we have chlorides this time substituting the water ligands. However, because the chloride minus ions are a lot bigger, so Cl minus ligands are much bigger than H2O ligands, even though they are also monodentate, that means that we can't fit as many of them around the cobalt. So can't fit as many Cl minus ligands around the CO2 plus, and that means that we can only form 4 coordinate bonds. And so it forms a tetrahedral shape. And because it's only got 4 coordinate bonds, that means its new coordination number is 4. So the coordination number goes from 6 to 4.